So since we mentioned a lot of math and a lot of physics, what do you use the difference between mathematics and physics as disciplines, as ways of understanding, of seeing the world? Maybe we can throw in engineering in there. You mentioned your wife is an engineer, give it new perspective on circuits.
Right.
So this different way of looking at the world, given that you've done mathematical physics, so you've worn all the hats.
Right. So I think science in general is an interaction between three things. There's the real world. Um, there's what we observe of the real world, our observations, and then our mental models as to how we think the world works. Um, so we can't directly access reality. Okay, all we have are our observations, which are incomplete and they have errors. And there are many cases where we want to know, for example, what is the weather like tomorrow, and we don't yet have the observation, and we'd like to a prediction. And then we have these simplified models, sometimes making unrealistic assumptions, spherical cow type things. Those are the mathematical models.
Mm-hmm.
Mathematics is concerned with the models. Science collects the observations and it proposes the models that might explain these observations. What mathematics does is we stay within the model and we ask what are the consequences of that model? What observations what predictions would the model make of future observations or past observations? Does it fit observed data? So there's definitely a symbiosis. Um, it's math. I guess mathematics is unusual among other disciplines. Is that we start from hypotheses like the axioms of a model and ask what conclusions come out from that model. Um, in almost any other discipline, you start with the conclusions. I want to do this. I want to build a bridge. I want to make money. I want to do this. Okay, and then you find the path to get there. There's a lot less sort of speculation about. Suppose I did this, what would happen? Planning and modeling. Um, Speculative fiction maybe is one other place, but that's about it. Actually, most of the things we do in life is conclusions driven, including physics and science. I mean, they want to know, where is this asteroid going to go? What is the weather going to be tomorrow? But mathematics also has this other direction of going from the axioms.
What do you think? There is this tension in physics between theory and experiment.
Mm-hmm.
What do you think is a more powerful way of discovering truly novel ideas about reality?
Well, you need both top down and bottom up. It's a really interaction between all these things. So over time, the observations and the theory and the modeling should both get closer to reality. But initially, and this is always the case. They're always far apart to begin with. But you need one to figure out where to push the other. So if your model is predicting anomalies that are not picked up by experiment, that tells experimenters where to look. To find more data to refine the models. So it goes back and forth. Within mathematics itself, there's also a theory and experimental component. It's just that until very recently, theory has dominated almost completely. Like 99% of mathematics is theoretical mathematics, and there's a very tiny amount of experimental mathematics. People do it, like if they want to study prime numbers or whatever, they can just generate large data sets. And so once we had computers, we began to do it a little bit. Although even before, like Gauss, for example, he conjectured the most basic theorem in number theory, which is called the prime number theorem, which predicts how many primes there are up to 1 million, up to 1 trillion. It's not an obvious question. And basically what he did was that he computed, mostly by himself, but also hired human computers, people whose professional job it was to do arithmetic, to compute the first 100,000 primes or something, and made tables and made a prediction. And that was an early example of experimental mathematics. But until very recently, it was not. Theoretical mathematics was just much more successful. Because doing complicated mathematical computations was just not feasible. Until very recently. And even nowadays, even though we have powerful computers, only some mathematical things can be explored numerically. There's something called the combinatoric explosion. If you want to study, for example, Zermani's theorem, you want to study all possible subsets of the numbers 1 to 1,000. There's only 1,000 numbers. How bad could it be? It turns out the number of different subsets of 1 to 1,000 is 2 to the power 1,000, which is way bigger than any computer can enumerate. In fact, any computer ever can enumerate. So you have to be there are certain math problems that very quickly become just intractable to attack by direct brute force computation. Chess is another famous example. The number of chess positions we can't get a computer to fully explore. But now we have AI. We have tools to explore this space, not with 100% guarantees of success, but with experiment. So like we can empirically solve chess now. For example, we have very, very good AIs that can, they don't explore every single position in the game tree, but they have found some very good approximation. And people are using actually these chess engines to do experimental chess. They're revisiting old chess theories about, when you this type of opening, this is a good type of move, this is not, and they can use these chess engines to actually refine, in some cases overturn conventional wisdom about chess. And I do hope that that mathematics will have a larger experimental component in the future, perhaps powered by AI.
We'll, of course, talk about that. But in the case of chess, and there's a similar thing in mathematics, I don't believe it's providing a kind of formal explanation of the different positions.
No.
It's just saying which position is better or not, and you can intuit as a human being. And then from that, we humans can construct
Yes.
a theory of the matter.